Hey everyone, welcome to Chegg's Gen Chem Office Hour. This is a weekly office hour that is brought to you by Chegg that is completely free. We want to see you in the chat. We want to see you sharing this feed. We want to reach as many students as possible. My name is Corinne. I run Chem with Corinne. I was a chemist. I remember the struggle of being a chem major. I liked chemistry so much so that I went on to get a couple more degrees in chemistry and I eventually became a chemistry teacher. So yes, I'm a total chem nerd. I am here running my accounts, embarrassing myself to try to teach as many of you chem as possible. So what these sessions look like is you just put your questions in the chat. Make sure you're sharing this feed with all of your buddies in chem who are also struggling right now so we can help as many students as possible because Chegg is just here to help you out. They have so many incredible resources. If you're not following their YouTube and TikTok, and I think they're on Instagram too, you need to do that. They have, reminds me, I need to go live on Instagram. But they have so many valuable resources for you. I had so much fun checking out Chegg Study. They have so many options, including like an assessment generator. So you type in your topic and they create 10 questions for you. And not only do they create those review questions, it will also generate the answers and information to help you understand how you get to those answers. So definitely check out Chegg if you have not. But let's go ahead and get started. I'm going to just be answering your questions for the next hour. So we're here every Monday at this time, and then there are 10 other sessions throughout the week. So if you're not following Chegg yet, please do that. All right, so last week I had a request to go through rate laws. There are a lot of questions about kinetics and rate laws. If that's not what you're here for tonight, put it in the chat, and that's what I'll jump into next. But let's go ahead and start with rate laws. So the big question is, how do I determine the rate law and the rate constant? So there are lots of different types of problems with this. We're going to start with just like the rate law. So we're going to look at experimental data. So if you're given a graph like this, you're going to have your concentrations of your reactants, and you're typically going to be given your reaction rate. Your job is to then identify places where the concentration is held constant versus where it is changed and see how that impacts the rate. So your goal when writing a rate law, right, is to determine the order with respect to the concentration of each reactant. So how does changing the concentration of each reactant affect the rate of the reaction? And the rate of the reaction is just like how quickly that reaction goes, right? All right, so looking at this one, all right, so right away you look at this graph and you're like, okay, in between trials 1 and 2, my ozone is held constant, okay? So therefore, if I look at my concentration of NO, right, if I look, I have doubled that. What happens to my reaction rate? It also doubles. Okay, so therefore that is going to be first order with respect to NO. So as I write out my rate, or my rate law, right, I'm going to have my rate constant, K, because we don't have enough Ks in chemistry. If you're doing equilibrium, you will know the struggle. But we have a rate constant, and then we want to figure out, so we know now that it is going to be first order with respect to NO. Like most things in chemistry, we do not actually have to include that 1, so we're just going to leave it as is. Now let's figure out what the order is with respect to O3 or ozone. So so between trials 1 and 2, we didn't change the concentration. But between trials 1 and 3, we half the concentration. All right, if we look at this and we look and we notice that the concentration of NO is held constant, then we'll have an accurate idea of how that change in concentration is actually impacting the rate. So that's a really key takeaway with this. You want to make sure that if you're looking at how the rate is changing with respect to only one of those reactants, right? If I'm changing everything here, I'm not really going to be able to pull out the information I need, or at least not easily, to figure out the order. All right, so let's look at trials 1 and 3. So I've gone from 2 times 10 to the negative 4th to 1 times 10 to the negative 4th. So I have reduced that by half. So my concentration has been halved. And if I look at my reaction rate, guess what? That has also been reduced to half of its initial rate. So it's going to be first order with respect to O3 as well. All right, so we have just figured out our rate law. Now let's say we wanted to know the overall rate or overall order of reaction. How do we do that? Thankfully, it's really simple. You're just going to add those exponents. So in this case, remember, we assumed we didn't actually put in the 1, right? But it's first order with respect to NO and first order with respect to O3. So therefore, our overall rate is just like you add up those exponents. So in this case, it's just going to be second order. All right, so that's what. So if we're looking at with respect to just one of the reactants, right? It's only first order with respect to either of these, but the overall rate order is going to be second order. All right, now this question says, okay, let's take this now and then determine the rate constant. And actually, it's really easy to do. Again, I think students get overwhelmed by kinetics and rate laws because you see all of these units and numbers that are typically really small. So when you're looking at numbers in scientific notation, you're like, oh, wait, like, what is that? Don't even worry about that, okay? We're just plugging in values. So if we want to determine K, I like to do the algebra ahead of time. Sorry, I'm going to erase that because it bothers me to have those ones there. We know there are ones there. Don't need to include them. I like to do the algebra first. So our goal is to solve for the rate constant. Let's rearrange our equation to solve for K. So we're going to say K is equal to, we're going to divide both of these by the concentration of our reactant, so our rate, over the concentration of NO times the concentration of O3. And now all you have to do is take one of these trials and plug the data in. Okay, so really easy to do that. Does not matter which one, you should get the same answer. Anyway, whichever trial you use. All right, so I don't know that I really need to write that out, but basically we just take this rate and then we divide by this times that to get our K value. And if we were to do that, let's go ahead and I'm going to write it out. I don't like leaving problems unfinished. I don't know. It bothers me. Let me know if you're in the chat and you want to see a different topic right after this. All right, so we have our rate. We have 4.0 times 10 to the negative 6. I'm actually going to write out all of my units because I think that's one of the hardest parts is figuring out those units for your constants, right? All right, so we have our concentration of NO was 1.50 times 10 to the negative 6. And our concentration at that time was 2 times 10 to the negative 4th. All right, let me just plug all of that into my calculator. When you're doing any type of problem like this, obviously that algebra was really easy. The easiest mistake to make is a calculator error with this. So whenever you have exponents in your denominator, make sure you're using parentheses. Otherwise, your calculator is going to divide by this first number and then multiply everything by just 10 to the negative 6. So just be careful with that. So as I'm saying that, I'm not like actually typing it in. I should be. Let me go ahead and do that. All right. If you can get this answer faster than me, please do, and put it in the chat for me. We're here to help each other, right? All right, so my rate constant is 1.33 times 10 to the 1, 2, 3, 4, 5, let's see, times 10 to the 4th. All right, so now looking at this, I did not do a good job because I didn't put my units underneath, right? So we have our moles per liter times moles per liter. So basically, this is going to cancel out. And we'd have our rate constant. So now we have to figure out what those units are going to be. So basically what we'd end up with, right? I'm just going to write out the units so you can see this because this is another thing that trips up students. So we have moles per liter per seconds divided by moles squared per liter squared. So really when I do the algebra, right, I'm going to end up multiplying by liters squared over moles squared. I'm going to cross these out, and I'm going to end up with liters per mole per second. And those are my units for the rate constant. I'd say that is the trickiest part because you are literally just plugging and chugging, right? Other than that. All right, so just a little bit with rate laws. So if you are asked, okay, now looking at this, why do I need that rate constant? What does that tell me? This is going to tell me how quickly this reaction proceeds. This is a very high rate constant. Therefore, we'd expect this reaction to be happening at a very fast reaction rate. And this is actually something that happens. This is how one of the compounds that reacts with ozone to deplete the ozone layer. So you can definitely look up. There's some really cool chemistry associated with that. All right, it looks like you are in the chat. So please put your questions in the chat. I am happy to talk through any topics related to Gen Chem tonight. If you are here and hoping for Orgo Chem, come back tomorrow night because there is another specific organic session tomorrow night. All right, it looks like I have a question on TikTok. Can you go over solutions and like parts per million and molarity? Yeah, let's do that next. All right, solutions and Yeah, so with solutions, there are a lot of different ways to determine the concentration of a solution. So let me back up. In case you are just starting solutions, right, you need to know a solution is just going to be a homogeneous mixture. So if I take salt, I add it to water, it still looks like water, right? You can't tell that there's anything dissolved in there. It is going to be what we call an aqueous solution, where you just have some kind of solute dissolved in that liquid. All right, solution concentration. All right, so the most common type of concentration you're going to have to calculate in any chemistry course is going to be molarity. So the molarity, it's a capital M, it's the moles of solute per liters of total solution. All right, so a lot of times you'll just see moles per liters. Another way to rearrange this equation, this is really helpful if you're doing titrations and things like that, is thinking of it as molarity times volume equals moles, or MV equals moles. Again, the capital M represents molarity. The capital V is the volume. Other things you might see molality. In molality, we're still looking at the moles of solute, but per kilogram of solvent. So solvent is what does the dissolving. That is the main part of your solution, typically, not always, versus solute is what is dissolved. So the easiest example that you can use to just connect to your real life is like making lemonade or Kool-Aid, something like that, right? So you take the powder, the drink powder, you add that to water. The water is your solvent, the powder is your solute, and then the total Gatorade or lemonade, whatever you've made, that is your solution. How do you know what is aqueous? Yeah, that's a good question. So let's say you're doing a precipitation reaction and you've been told that one thing is a precipitant. You are going to form that precipitate, right? The solid suspended in solution. How do you know what that product is going to be? It's all about knowing your solubility rules. And I can go through that in just a second. So that question just came in from TikTok. I will come back to that. So I'm going to go back. So can I go over solutions and like just molarity? All right, so let's just do a simple molarity calculation. Another type of, so I was talking about molarity, molality. There's also parts per million. Lots of different ways to represent just the concentration of the solution. So whenever you're doing any of those, just making sure that you are in the correct units is the most important part with this. So let's just do a sample solution calculation. So determine the molarity if 5.2 grams of copper 2 chloride I'll say are used you have to be careful with your language with these types of problems. So again, with molarity, we're looking at the total volume of the solution. So if I said, if I just said like 5.20 grams of copper 2 chloride were added to 150 milliliters, technically that solid has volume, right? So you got to be really, really careful with that. All right. So what do I need to do to solve this problem? First thing, I want to figure out what it's asking, right? I'm trying to find the molarity. I have 5.20 grams of copper 2 chloride and I have my volume. All right. So I know my volume is 150 milliliters. I have to change that into liters first. So I'm going to divide by 1,000. That becomes 0.150 liters. That is my volume. That is ready to go. Do I have my moles of solute? No. Okay, so what you have to do with this is you have to quickly convert your mass into moles. So I'm going to take my 5.20 grams. I want to convert from grams of copper 2 chloride into moles. Whenever I'm doing this type of conversion, right, I'm going to put the grams, the unit I'm converting out of, in the opposite position. So it's in the numerator originally. I'm going to put it in the denominator. And then what I'm looking for is the moles of copper 2 chloride. Notice I haven't put any values in with this. Always start with your units, then work your way back into the numbers. So in 1 mole, how many grams is that equal to? I don't have that off the top of my head. Let me calculate that molar mass. So I'm going to find copper. Copper is 63.55. And then that has 2 atoms of chlorine. So I'm going to say 2 times 35.45 gives me 134.45 grams. All right, so anytime you're given the grams and you need to convert that into moles, you always end up dividing by that molar mass. So I have 5.2 divided by 134.45. That gives me 0.03868 moles of CuCl2. All right, so we had to do that, right? We had to change that into moles first to be able to calculate that concentration. Again, I think I'm down at the bottom of the screen, so let me move that up. The concentration is the moles per liter. So I'm just going to take that number, 0.03868. I tend to round for sig figs at the very last step. That's why I'm carrying so many right now. Okay, divided by my volume. So notice my units. That's the biggest thing with this. I'm taking my moles, dividing that by my total volume of the solution to find out that I have a concentration of 0.25784 molar. So now let's go back. Let's figure out how many sig figs we need to have with this. And then I'll go back and we'll talk about how do I know what is aqueous in a solution. All right, so looking at this, you always look at your initial values in the problem. That's what's going to determine your final sig figs. So looking at this, my mass had 1, 2, 3. That 0 is significant because it follows non-zero numbers. And then with my volume, I also have 3 sig figs. So when the decimal is present, you come in from the Pacific side or the left side. All 3 of these, including that 0, are significant. If I did not have that decimal point, so if I just had 150 milliliters, this would only have 2. Okay, so that's what's so tricky about sig figs. But everything has 3 sig figs. Therefore, my final concentration should also have 3. I'm going to round at the 7. So this becomes 0.258 molar as my concentration. All right, so just a little bit about concentration. Again, there are lots of different ways that you will have to calculate the concentration. Just be careful with your units. Everything, it's pretty much the same process. I would say molarity and molality are probably the 2 most common. So with when you're doing lots of problems in between those 2, just be careful, right? So remember that with molality, you're looking at the kilograms of the solvent only, which is very different from the concentration. All right, so how do I know if something is aqueous? Let's just do a quick precipitation or net ionic reaction example. And then it looks like I had another question on TikTok about Lewis structures. We'll do that next. Keep putting those questions in the chat. We are here until 9:30 tonight, Eastern time. So we are here for the next about 45 minutes, just answering any and all of your Gen Chem questions. So keep putting them in the chat. Keep sharing this feed. Cheng and I want to help as many students as possible. So thank you to those of you who are here tonight. All right, let's just do a quick precipitation reaction. And while we do that, let's do some balancing too. Why not? All right, so we have, let's say we have silver nitrate. I don't know why I put a solid. That should be aqueous. Reacting with, let's do, okay, with calcium bromide. So how do we know what is aqueous? How do we know what the products are? How are we going to figure this out? How do we know what that net ionic equation is going to be after I have my full double replacement reaction? So with this, there are a lot of different ways to look at it. I tend to have my students look at the metals. So the first element, those cations in these 2 compounds, those are just going to swap partners basically. So they switch places. So in my new compound, I'm going to have silver bromide and then calcium nitrate. Doesn't matter the order that you put them in. What matters is that you're putting your metals first and you're making sure that you're canceling out based on the charges. So you've got to go back to like ionic nomenclature. There's a lot involved with it. All right, so I have calcium. Calcium has a charge of +2. Nitrate has a charge of -1. So this is going to form CaNO3 2. I'm not going to worry about states yet. I'm just going to be worrying about my products. The other product is going to be silver bromide. Silver is one of your transition metals that actually has a designated charge. It is always +1. Bromide is a halogen, so it has a charge of -1. All right, now I'm going to go back and worry about what is aqueous and what is not. What is my solid precipitate? All right, so what I tell my students is remember what is always soluble. So anything from group 1, any acetate, anything with ammonium, or anything with nitrate. So already looking at this, I see, oh, this is nitrate. That's going to be aqueous, okay? So I'm going to do AQ here. And then that means if this is a precipitation reaction, that has to be my solid. So I think the best way to do this, right, is just to say, okay, focus on what has to be aqueous. If I see something with sodium or potassium or nitrate, that is my aqueous product. That means the other thing has to be the solid precipitate. If you want to memorize all of the rules, NAG, SAG, PMS, Castro-Bear is the best way to do that. All right, if I want to then write out my net ionic equation, I'm just going to focus on the formation of my solid. That is it. So I say, okay, write out your solid product first, and then work backwards to see what you need to build that solid. So I have 1 atom of silver and 1 atom of bromine. Not too bad. All right, so just a little bit on net ionic equations. It looks like everyone is asking for Lewis structures in the chat, so that's what we're going to do next. We'll do Lewis structures, and then we'll talk about some electrochem, it looks like. So keep putting those questions in the chat. We are here to help you. Anything related to Gen Chem. If you are not here for Gen Chem, know that there's an organic session tomorrow night. And then there are multiple Gen Chem sessions all week. So there's a Wednesday night stoichiometry session, and then there's another Gen Chem session on Thursdays. So please check them out. And there's a question on the TikTok about, can you go over mechanisms and the rate law expression? That's actually what I started the session with. So if you hop back onto YouTube after the session, you can start right at the beginning, and that's where we started. If I have some time, I'll go through like rate graphs after that too. All right, so let's just do some Lewis structures. All right, let's do ethanol. Let's say you had to draw a Lewis structure for this compound. So the best thing to do, yeah, I agree. So someone just hopped in the chat and said Castro-Bear is a great way. Yeah, so NAG, SAG, PMS, Castro-Bear is a great way to remember those solubility rules. Definitely check it out. I know Chegg has a great video on their TikTok channel that goes through that mnemonic to help you out. All right, so Lewis structures. Let's talk Lewis. I feel like this is a weekly request because it is a hard thing to just like to really understand and do well at. And this is one of those topics that it's not math-based in chem, so it's a little tricky because of that. It just takes practice. The more you're exposed to these different compounds and the types of compounds, the easier it gets to determine these Lewis structures. And unfortunately, if you're just starting to learn Lewis structures, you will have to keep coming back to them. So definitely invest in this and this process and take some time to master it because you will need it all year long. All right, so if I want to draw the Lewis structure, first step, you always want to count total valence. All right, so I'm counting total valence electrons. You can determine that just from the periodic table. So it's all determined based on the column the element is in. Please note that everything in the transition metals, right, has varying numbers of valence electrons, but guess what? For Lewis structures, you're only doing covalent molecules, so you don't have to worry about any of those metals anyway. All right, so I'm going to look at this. I have carbon. I have 2 atoms of carbon. We'll just add them up. So I have 4. Each atom of hydrogen has 1. I have another carbon atom, 2 hydrogen atoms. Oxygen has 6. And then I have another hydrogen atom at the end. And a common question is, wait, why is it written like this? Why isn't this just C2H6O, right? And technically, either one of those is correct. The way it is written right now, though, is going to help you with your structure as we're trying to figure out what that carbon chain is. So this is an organic compound, which is just going to be a carbon-based compound. All right, so I have 4 plus 3 plus 4, so that's 11, 13, 14. I have 20 valence electrons in this compound. So that's always your first step. Count the total number of valence electrons. Second step, you're going to draw a skeleton structure. What do I mean by that, right? So you're pretty much just going to predict how these atoms are going to bond together. So drawing bonds between elements. All right, so with this carbon, you have to think about how many valence electrons each atom has, and that's going to help you determine how those bonds are going to come together. So carbon has 4 valence electrons. Everything, for the most part, wants 8. So that means it's going to need to form 4 bonds. Hydrogen only has 1 electron to share. It can only form a single bond. You're never going to have hydrogen in between two different elements. It also is never going to have any extra electrons. Thinking about your halogens on the opposite side, right? They have 7 valence electrons. Guess what? They only want 1. They will only form 1 bond as well. Versus oxygen, 1 to the left of that, has 6 valence electrons. How many bonds does it want to have? 2. So just like knowing those little tricks definitely helps too. So let's go ahead and just kind of predict how this is going to look. So I'm going to put carbon. Carbon is going to have 4 bonds. I'm going to put hydrogen at 3 of those spots. And again, this kind of shows me like what's going on here. And then that's going to connect to another carbon, which also is going to want to have 4 bonds. So I'm going to put in those 2 hydrogens. I'm going to put an oxygen and then a hydrogen. All right, step 3. Now that we've drawn that skeleton structure, fill in extra electrons to satisfy the octet rule. All right, and let me know. Call me out in the chat if this is way too small and you can't see this. All right, so I have just drawn a skeleton structure. Obviously, not everything has all of its electrons. So if I had halogens, if I had a chlorine hanging out over here, I need to put in 6 electrons around it. Each of these lines only represents 2 electrons. So basically, with these bonds, I'm showing 1 electron from oxygen and 1 from hydrogen. But in this case, so both of these have those 2 electrons. So I'm just going to run through and count. Hydrogen has its 2 in all of these spots. Hydrogen looks good. Carbon has 2, 4, 6, 8. 2, 4, 6, 8. Both of my carbon atoms look good. But what's missing around the oxygen? Right now, the oxygen has only 2 bonds. That means it only has 4 electrons technically. So I'm going to have to draw in those lone pairs. So there's those extra electrons that are not bonded or not shared in a bond. So those lone pairs are going to go above and below oxygen. Now, last step is I'm just going to double check my total. And this is where you end up adding double and triple bonds as needed. All right, so now looking at this, let's go ahead and count everything up. So I'm going to draw little dots so you can see where I'm counting. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So everything has the 20 electrons, and then this is good. All right, so those are the 4 steps for drawing a Lewis structure. I'm going to go ahead and do another one since I did just have 2 requests in the chat for this. Let's do one with double bonds so you can see the difference between that. And I'll leave the instructions up. So if you want to screenshot that, you are welcome to. Probably when I move out of the way, right? Let's do HCN. So notice, again, with Lewis structures, you're always going to be looking at molecular or covalent compounds where those electrons are shared. All right, so first thing we want to do is count our total valence electrons. Again, valence is dependent on the column that each element is in. So hydrogen is in that first column. It's going to have 1. Carbon has 4. And then nitrogen has 5. So that gives us 10 total electrons to work with. Now we want to draw a skeleton structure where we're just going to kind of predict how these elements are going to come together. All right, so we have carbon in the middle. Carbon needs to have 4 bonds. And right now there are only 2 elements for it to bond with. So let's look at this. We want to fill in extra electrons to satisfy the octet rule. So already I'm looking at this and I'm like, oh, wait, is carbon going to have extra electrons? No, carbon has 4 electrons, right? And nitrogen has 5. So already I'm noticing, I'm like, oh, wait, what are these guys doing here by themselves? Like, they're not going to be happy with that. So this is a case where you'd look at this and you'd say, oh, wait, I am definitely going to have maybe a double. Nope, I'm going to have a triple bond with this. So now looking at this, I'm going to have it set up like this. So basically now carbon has the 4 bonds, nitrogen has 3 bonds for a total of 8 valence electrons. Carbon also has 8. So we have 2, 4, 6, 8, 10. that one checks out. All right. So that process of trying to identify where we're going to have those double and triple bonds definitely takes time, but with time you get there. It looks like we had a question. Can you demonstrate an example when an element has an expanded octet? Yeah. So there are situations, right, where we're going to have what's known as the expanded octet. So let's look at, I don't know, sulfur hexafluoride. All right, so with this one, the process is still the same. So if you are not familiar with this, an expanded octet is when the central atom has more than 8 valence electrons. And if you did not know that could happen, I'm sorry to like ruin your world, but yeah, it can happen. It's called hypervalent. So if an element is hypervalent, it just means that it can have more than those 8 electrons. All right, so let's look at sulfur hexafluoride. So sulfur, same process. So sulfur has 6. We have 6 atoms of fluorine. Each one has 7 electrons. So we're going to have 48 electrons to place. So already you look at that and you're like, how is this even going to be possible? Just wait. Let's do this. All right, so we want to draw a skeleton structure. So I'm going to put sulfur in the middle. And guess what? I am literally just going to draw fluorine atoms all around it. So we're just trying to figure out how this is going to work. Why am I not putting like one fluorine and then another one? Because fluorine is a halogen. It has 7 valence electrons. It only needs that single bond. It's not going to have additional bonds. All right, so now looking at this, now we're at step 3. We want to fill in extra electrons, typically on those outer atoms, to satisfy the octet rule. So get ready for some arts and crafts here. I'm going to add in 6 electrons around each atom of fluorine. All right, and now my last step is I'm going to double check just the total by seeing if it all adds up. So right now I have 8, 16, 24, 32, 40, 48. So this checks out. All right, so this is just an example of the expanded octet. So basically what this means is when I go to do the geometry, it's going to look slightly different. I think I even have one here. This is only 5. Oh, here it is. All right, so this is known as octahedral geometry. So it's a little bit different if you've only been looking at through tetrahedral. Just means that you have 6 bonds around that central atom. All right, so I hope that was helpful. A couple examples of Lewis structures. I'm going to jump back into the chat. Keep asking those questions. We just want to help as many students as possible. We're about halfway through our session tonight. Keep sharing the feed. Let me know what you're working on right now in chemistry, and that's what we'll cover tonight. That's what we're here for. I think I had requests for some electrochem, so we'll talk through voltaic cells next. And that's also what's fun about these sessions. So if you happen to be here on the replay, or if you are here right now and you're like, I'm not learning electrochem, it's okay. We'll switch and we'll do another question after this. You can also find all of the replays on my channel, Chem with Corinne, and you can also find them on Cheg's channel. So use that. I always drop a comment with all of the tags for each of the topics. So you can go back and find examples from the topics you are currently covering in class. So know that that's also an option. All right, so electrochem, we're going to look at voltaic cells. All right, what do you need to know about a voltaic cell? There are a couple things. The first one is that you have to have a salt bridge in a voltaic cell. And if you happen to be taking AP Chem, for some reason, this is a favorite question on the FRQ. So what do I mean by a salt bridge? Let's make it potassium nitrate. So this is called a salt bridge. It just allows us to balance the charges. All right, so let me go ahead and draw my solutions. You can tell I am not an artist, but we'll make it work. All right, so let's draw our electrodes. I'll have our little voltmeter. All right, so in a voltaic cell, this is going to be a cell that is favorable. So it is thermodynamically favorable. We're going to have a cathode and an anode, a couple mnemonics to help you with this because I think it's so hard just to remember all of the terminology and whatnot. So when you're doing a redox reaction, right, you have to remember a couple things with these cells. So oxidation versus the reduction. So like the locations of these, where does it happen in this cell? Oxidation, if you can remember, oxidation happens at the anode versus red cat. Reduction happens at the cathode. So with that, you also want to remember that electrons come to the cathode, they move away from the anode. And with a lot of these questions, you're going to be asked to find the total cell potential. So you're looking for a positive value with a voltaic cell, because again, this is a thermodynamically favorable process. I want to go back. I saw that question in the chat just a couple minutes ago, so let me make sure I'm answering that one all right. So please explain voltaic cells. Yeah. So that's basically like a little bit about voltaic cells. Again, knowing that they need the salt bridge to balance that charge, electrons move away from the anode and come to the cathode. And because of that, the cathode, the mass of that is going to change as the cell runs. Eventually, the cell, it can't run for forever, right? Once you have all of those ions changing, the concentration changing, eventually the cell will be dead. A dead battery is basically the cell that the reaction has just gone to completion. So those are just a couple of things. Know that we have standard conditions with these. If you are at conditions other than 1 molar for your concentrations, then you're at non-standard conditions with that. I don't know. I think that was just a broad overview of voltaic cells. If you'd like more specific examples, please let me know in the chat and I can just do like a practice problem with this. And I'll definitely, you know what, how about I'll plan on that the beginning of next week's session. It's really fun doing these sessions because everybody, just depending on which class you're taking and where you're taking it, everybody is just kind of at a different point. So like I said earlier, if you are watching this and you're like, oh, wait, I need help with this, please check out our pages. So both Chegg and I have all of the replays listed, and you can find timestamps with each of the different topics. So if you're like, wait, I want more help with Lewis structures, go back earlier in the session or look at the last couple sessions. We do that just about every time. All right, it has a question. Let's see. Yeah, I guess I'll go back to TikTok. So we had another question. Can you go over the mechanisms and the rate law expression? So please watch the replay on that because that's where I started. But we can talk through like the graphs and how we use those to figure out the order of the reaction. So let's say I had, let me think of a reaction real quick. And as I'm writing this, let me know. I want to know, like, which class are you taking right now? Are you in Gen Chem 1, Gen Chem 2, or AP Chem? So let me know in the chat so I can have an idea. So the more you guys put in the chat, the better these sessions are going to be each week. So please kind of let us know so we know which classes to prep for. All right. Let's see. All right, so let's think about a different reaction. So earlier we looked at ozone reacting with nitrogen monoxide. Let's look at the decomposition of nitrogen dioxide now. So I have NO2, and that's going to decompose into NO and oxygen. All right, so this is just one of those reactions happening in our atmosphere. Let's go ahead and balance this reaction. What type of reaction is this? This is going to be a decomposition reaction. It looks like we had someone in the chat. Yeah, that's another great mnemonic. So someone on TikTok just said, oil rig, oxidation is losing, reduction is gaining. Yeah, so oxidation is loss of electrons, reduction is the gain of electrons. So that's a really great way to remember all of those mnemonics. And you know what, next week, what I will do is I will start with an electrochem example, and we'll just run through all of those mnemonics so you have them. Because it's tricky because it all feels counterintuitive. But thankfully with rate laws and order of reaction, it's a little bit more clear cut. So let's look at that. So again, this is a decomposition reaction. I'm taking a single reactant, breaking it into multiple products. Let's go ahead and balance this reaction first. I have NO2 here. So I have 2 atoms of oxygen on the left side, and I have 3 on the right. Let's go ahead and put a 2 in front of this. Now I'm going to have to make a 2 here. That gives me 2 atoms of nitrogen, which checks out with the 2 atoms of nitrogen there. I have 4 atoms of oxygen, because again, if you have a coefficient in front, that tells you the number of molecules. So I have 4 atoms of oxygen, plus on the product side, I have 2 plus an additional 2. That also gives me 4. So I'm good there. All right, so now that I have that balanced, I'm just going to like make up a problem. Let's say, okay, my question for you is, can you determine the order of the reaction if I give you just some data? All right, so let's say I have some experimental data for you. So I have the rate in relation to the concentration of NO2 over time versus the natural log of NO2 over time versus 1 over the concentration of NO2 over time. And hopefully you are like wiggling in your seat right now. You're like, I know how to solve this. I got this. All right, so let's say this curve looks like this. This one looks like that. And this one looks like that. All right, so looking at these 3, how can I use this data to quickly determine the order of reaction? Unfortunately, this is one of the things you have to memorize in any like first year chemistry class, right? So knowing that the order of the reaction, so if you graph these, so you don't have to necessarily remember the rate laws, the rate mechanisms, right? If you can remember that the straight or the linear curve is going to represent the correct relationship. So in this case, this is going to be second order with respect to the concentration of NO2. I know this because I have a straight line here where my slope is equal to the negative rate constant. So looking at this, if I had a first or a zero, I did not do that right. This should be first order. My bad. All right, it happens sometimes when you're in front of a whiteboard. Try it out. You make the most ridiculous mistakes. So if I make a silly mistake, call me out on it with the chat. Like that's why we do this. All right, so if I have a 0th order reaction, I would expect to see a linear curve. If I have a first order reaction, I would expect to see a linear curve with the natural log of whatever that reactant is. Versus if I have a second order reaction, you will see a positive slope, but it will still be linear if you graph 1 over the concentration over time. All right, so basically we can use the experimental data to quickly see the order of the reaction with regard to that concentration of that reactant. So just a different way to do this. All right, so a little bit of everything tonight. Thank you all for being here. Let me know how else I can help you. We have 17 minutes left tonight. I was ready to do some thermo because we had a lot of requests for thermo last week, and also some acid-base chemistry. Do you guys want to do that? Let me know. You decide what I'm doing next. And really, the more feedback you guys give us, the better these sessions will be. So let us know which chemistry class you're taking right now, what you're studying, and which topics I should prep for next week. Because whatever I don't get to this week, that's where I start next week. And I spent a couple hours every Monday just trying to get some really good problems for you so that we can go through a lot of different topics. Let's see. And recently I have checked out Chegg's assessment feature. It is so cool. If you haven't checked out Chegg's study yet, you definitely need to. You literally just type in a topic and then boom, you have a 10-question quiz built out for you with answers, with everything. Yeah. Yeah, that's a good question. Why do we need to learn the order of reactions? So you need to know how the concentration of various reactants impacts the rate of the reaction. It's also useful for understanding whether a reaction is going to be fast or slow. I don't know. I don't have a great answer for that because I'm not a huge fan of reaction kinetics. But yeah, it's one of those topics. It's like, You just have to learn it. I wish I could really talk to you about the applications of it, but you know what? I'm going to look into that and get back to you because it's not my favorite topic. Yeah, and if anyone has a better answer, I feel really guilty saying that because I'm one of the people who's like, no, there is a reason for everything you learn in chemistry. Yeah, well, except for this and probably electron configuration. Not a huge fan of either of those topics. All right, I need help with polarity and IMF. All right, Sophia on TikTok, this one's for you. So IMF and polarity. So earlier we looked at ethanol. Let's go ahead and look at that compound again. So we have CH3, CH2, OH. So I'm going to go ahead and draw that Lewis structure again. If you need help with Lewis structures, jump back and watch the replay because we did go through this one. So I have CH3, CH2, OH. All right, so I'm looking at this compound and I want to make some decisions about it. I want to know what type of intermolecular forces it experiences. I also want to figure out, is it polar, right? And what do I mean by is it polar? So looking at this, I have CH bonds, I have C to oxygen bonds, and I have an oxygen to hydrogen bond. So when I'm thinking about IMF, there are 4 types of IMF that you need to know. So we have ion dipole, we have dipole dipole, hydrogen bonding, really deceptive name because it's not a bond, it's still an intermolecular force, and we have London dispersion forces. All right, so first thing I need to know to be able to answer whether this experiences any of these intermolecular forces is whether or not it is a polar molecule. All right, so with polarity, right, we have to look for differences in electronegativity. So you can think about the trend on the periodic table with electronegativity. My silly periodic table. All right, fluorine is your most electronegative atom. So this is my increasing electronegativity. So basically, that means that fluorine in a covalent bond is going to have the strongest attraction to those electrons. It's going to kind of pull the electrons towards itself. It's not really the best way to describe it. It's going to shift the electron density towards fluorine in a covalent bond. Right. So thinking about that, basically what you have to do is you have to either look at the location of elements on the periodic table, or you use the table of values. You're looking for a difference in electronegativity that is greater than 0.4. So if the difference is greater than 0.4, that just means that there's enough of a difference between the two elements that the electron density will shift towards the more electronegative atom. So to let you know, the carbon to hydrogen bond is nonpolar. If I could, I would have all my students get that like in a temporary tattoo, because you need to know that is like one of the most common. Carbon to hydrogen is nonpolar. What that means is that the carbon to oxygen bond is polar. I don't have a chart of electronegativity values. I just know this. And then the oxygen to hydrogen bond is also polar. So normally when we're looking at a molecule, we're going to look at each of these. I'm going to go ahead and draw that in a different color. So our more electronegative atom is going to have the partial negative charge versus the other atom is going to have the partial positive. So in this case, the carbon. Notice none of these hydrogens have partial positives. That's because carbon to hydrogen is a non-polar bond. Please be careful with that. What that means is if you just had like methane, I live across the street from a bunch of cows. I'm really familiar with this compound. But if you have methane, is this going to experience hydrogen bonding or dipole-dipole interactions? No, because it is nonpolar. So just be really careful with that. So we'll talk about, sorry, I'm jumping around. I apologize. All right, so we have determined that we have polar bonds in this molecule. It is not a symmetrical molecule. Therefore, this is going to be a polar molecule. So what that means is we are going to experience differences in electronegativity where we have the slight shifting of those electrons, making partial positives and making partial negatives and leaving locations that are going to have a partial positive charge. All right, so looking at that, I know right away it's going to experience dipole-dipole interactions because it is a polar molecule. It is not going to experience ion dipole interactions, though, because those only happen when you dissolve an ionic substance in a polar medium. All right, so I'm not dissolving an ionic substance. Ethanol is just a polar substance, so this is going to be dipole-dipole. So now the question is, in addition to dipole-dipole interactions, does it experience hydrogen bonding? So hydrogen bonding, again, it is not a bond. It's just an interaction between a partially positively charged hydrogen and a very electronegative atom, which can be either oxygen, nitrogen, or fluorine. So again, let me repeat that. Hydrogen has to be in a polar bond. So these hydrogen atoms, right, are not going to experience hydrogen bonding because they are bonded to carbon. This hydrogen, however, will. So if I have additional molecules of ethanol, right, and you will, the oxygen is going to react, it's going to interact with the hydrogen in another molecule, right? So we're going to have those interactions coming in. This carbon is not as easy to get to. We call that steric hindrance. But this is a really good site for hydrogen bonding here. And let me just clarify, intermolecular forces are interactions in between molecules. So IMF are typically those intermolecular forces. Intramolecular forces, those are the bonds within, because the prefix intra means within. So those would be your covalent and ionic bonds, etc. All right, so these are just my hydrogen bonding. So I do have a site for hydrogen bonding, so I would expect that. And then everything experiences London dispersion forces, literally everything. So London dispersion forces are just based on this idea that electrons are randomly moving. So as they are randomly moving, they're randomly going to end up congregating somewhere, leaving a partial positive wherever they are not. So everything experiences this. The strength of the London dispersion forces is going to be based on the size of the electron cloud. So we call that, officially, we call that the polarizability of the electron cloud. And it's just this idea that the more electrons you have, the more significant that difference is, right, when they all end up together. With the strength of dipole-dipole interactions, these increase with the strength, increasing polarity. And I think that's all you really need to know with that. All right, so just a little bit. That was for Daisy CEE on TikTok. That was just a little bit of help with polarity and IMF. With these types of questions, too, you'll have a lot of questions, sometimes multiple choice questions, where you'll have two of the structures in front of you. One will have a really high melting point, one will have a low melting point, and you're like, what is the difference between these? Typically, it's going to be how many hydrogen bonding sites they have. If something has a lot more locations for hydrogen bonds are going to be the strongest interaction after ion dipole interactions. The stronger those intermolecular forces are, the harder they are to disrupt, right? So if I'm shifting from a solid to a liquid or to the gaseous phase, right, I have to break all of these interactions in between all of these molecules. The more interactions you have, the more energy that's required. Therefore, the higher that melting or boiling point is going to be. All right, let's see. A few more questions on TikTok. Okay. Yeah, so talk about electron withdrawing and donating groups. Come back tomorrow night. So that's not really something we talk about in Gen Chem, but that is a hot topic in Orgo. So come back tomorrow night for the organic session to talk about that. Let's see. Patrick on YouTube, I guess you probably took AP Chem last year, or maybe you took the ACS exam. Yeah, for some reason, intermolecular forces were not as popular as they normally are, but this is IMF. They're one of those topics that they impact so many physical properties and things like that. So a lot of times you'll have a big free response question, and at least like two of the portions of that question will be associated with the IMF. So just note, they just keep coming back. So understanding the definitions of all four of these and really being able to pull out where you would see hydrogen bonding, understanding how to determine whether a molecule is polar or nonpolar, those are all really helpful skills. All right, it looks like we had a question on Le Chatelier's principle. We can do that as well. We have 6 minutes left, so if you have any other requests, please put them in the chat. And like I said, whatever I don't get to tonight, that's where I'll start next week. So start spamming us with your comments and requests for next week, and that's where we will get started. All right, Le Chatelier. I don't have a question prepped for this, but it looks like maybe you just want an explanation. All right, so let's just talk about Le Chatelier's principle for a few minutes. So it's this idea. I think the easiest analogy is thinking about our system and all of the systems regulating our body, right? This is not like completely, it's not like the best. I don't know. We'll just talk through it. All right. So thinking about like when you start shivering, right? You step outside, it's cold. You start shivering, right? Because you're trying to regulate your temperature. Le Chatelier's principle is a similar design, right? So basically, a system at equilibrium wants to stay at equilibrium. So if I have a buffered system, right? If I have a weak acid and its conjugate base in a buffer system and I dump a whole bunch of strong base in there, they are going to interact to try to counteract that so my pH doesn't immediately skyrocket. So Le Chatelier's principle is just this idea that we can make predictions about how equilibrium is going to shift when we stress the system. And by stress, I mean we change the temperature, we add more reactant, we add more product. Just we change the pressure of the system. So basically we can create these changes to the system and then make predictions about whether the forward or the reverse reaction is going to be favored based on that. So let's say, just for example, I increase the concentration of my reactants. What's going to happen to counteract that is I'm going to make more product. If I do the opposite, I increase the concentration of my products, the reverse reaction is going to be favored because that product is going to be changed back into reactants. Because again, the goal is just to get this like a spot where we're at equilibrium still and we're not really noticing all of those changes. All right, so just a little like brief overview of Le Chatelier's. Let's see, I have a bunch of questions coming in. Yeah, so I have a question just about talk about pH and the equivalence point and midpoint and whatnot. Yeah, absolutely. All right, so let's do that. And I apologize. I don't think I have a bunch of questions coming in right now. Last few minutes. Come back next week or drop them on the replay of this. You can do that on my channel or Cheg's channel, and I will write all of them down. And that's what we'll start with next week. I love answering your questions too. So if you have questions or video requests, like I just do this for fun. I love to teach chemistry. I love to make it as relatable as possible. And Chegg is here and wants to help you out too. So please just keep dropping those questions in the chat and we will do what we can. And we're here every week, same time, same place. So put it on your calendar so I can help you next week. All right. So let's see. Can we talk about pH, the equivalence point, and midpoint and whatnot? Yeah. Let's talk about titrations. And let's just do like terminology. I think that's what that question is. So we had a question on TikTok. Can you talk about can you talk about pH, the equivalence point, and the midpoint and whatnot? All right. So when I am doing a titration, you're looking at a titration curve. There are some things that you need to know, right? So when I'm looking at a titration curve, let's say I'm doing a strong acid, strong base titration. So let's say I have hydrochloric plus sodium hydroxide. So you have your pH on the y-axis. You have your volume of titrant added on the X. So in a strong acid, strong base titration, my equivalence point is going to be at a pH of 7. Would help if I could draw a straight line. All right, so I'm going to have this point. This is known as the equivalence point. And notice I'm drawing this first. Your equivalence point is going to fall at the vertical point of the curve versus my, after that, I will have a pH above and a pH below. All right, so just this, we're going to have a vertical point in the middle. And this is where your moles of acid are equivalent to your moles of base. In a strong acid, strong base, that's always going to happen at a pH of 7. Versus if I switch this up and I want to do a weak acid plus a strong base, it's going to look slightly different. All right, so let's say I just have HC2H3O2. I know I'm running out of time, so I'm going to try to speed through this. So I'm still going to have my equivalence point here, but it's not going to be at a pH of 7 because this is my strong base. My pH, my equivalence point is going to be slightly above 7. I'm still going to have a vertical point here. And then the difference is I'm going to have a slightly different point too. So let's say this is at 40 milliliters. I'm also going to have what's known as a half equivalence point. I think that's what that question was referring to, the midpoint idea. So at the half equivalence point, half of my moles of acid are equivalent to half of the moles of base. So we'll have different points in the curve here. I'm totally running out of time. This is what's known as the buffer zone. And this is where my pKa is equal to the pH. I think what I'll do next session is I will just run through let's do it like weak-base strong acid titration. So I'll talk to you about each of these points, like let's calculate pH here versus here versus here versus here versus there. All right. So come back next week and we will do that. I will save all these questions in the chat. Thank you for being here tonight. And we hope to see you back next week. So thank you all.